First of all, I wanted to thank you, Carol, for the introduction. It was very kind of you, and definitely this series has been very, very special in many ways. It had definitely brought a lot of expertise and know-hows into the design and practicing internationally. The project has been really, this project, Lakhta in particular, has been really a melting pot of a global expertise who had really brought their best practices and international standards and technologies to deliver this project to the highest standard of equality and safety. It has been really an exchange of technology. I remember when the first time we started this project and we went to Russia, they did not use some of the latest technologies that we have, and we introduced a few of them in which we had to go to the building authorities and ask for a technical brief and a technical approval to use such document. But also I would like to thank our client, Gazprom, for giving us the opportunity to contribute to this project's success. My name is Ahmad Abdelrazaq. I'm the Executive Vice President with Samsung CNT and Project Executive for Lakhta Center. Again, just to briefly, this project has really very interesting stories. And essentially, it was a competition, as you can see from the screen, very well-known international architects, from Herzog to Daniel Lipskins and OMA, Jean Nouvel, and also RMJM. And RMGM definitely won the competition. As you can see, the shape of the tower is similar to the shape of Gazprom flame, essentially, which is a symbolic of the company. Now the project is really, excuse me, I'm having a little bit of the trouble on the screen here. Okay, so essentially the tower is a multi-functional complex built in St. Petersburg, Russia, consisting of the tower, the multifunction building, and the arch. And the arch, the main entrance to the building, in particular the tower. And then we have a very large open spaces that is left to the public, and especially for the amphitheater that is open to the view of the Gulf. This is an overall plan showing the three major components of the building, which is the tower, the arch, and the multifunction building. And this is the amphitheater here. And we have the North Plaza. It's also open to the public use. The multifunction building in particular, it has a science museum, exhibit hall, retails, medical center, multi-transformable halls, cinema, sports centers. It's a very complex element in its own right. During this presentation, I will not have much time to talk about this because of the limitation on time. And then and I will focus on the tower itself. And the main arch itself is a very long span structure, which is about 98 meter completely open span. And I'll briefly describe that during the presentation. This is here the completed building, as you can see here, the three major components. This is a later picture, an older picture, but the new one does show the plaza is nearly completed. Also, the project in itself, it has a very interesting history. Initially, the project was proposed in 2006 to Central Business District in St. Petersburg itself. And there was a huge amount of concerns, both locally and internationally, due to the historic nature of the building. And finally, Gazprom decided to move the tower about 9 kilometers away from the central business district. That's one of the reasons you will see to be a lonely tower right now. But this tower was the location has been strategically selected since it is very well connected. As you can see, most of the roads, new roads have been constructed, tram lines, metros, very close to the airport, railway stations, and so on and so forth. So it's a pretty good location, and I think it will be, as you will, a center to bring a new city, to take the burden from the old city and take it out into this present location. As you can see, the connectivity is very important. As you can see, you can reach the tower in many different ways. We're expecting at peak time more than 8,000 people to be coming into the site, and 50% will be coming by the metro. Now, the tower itself is 462 meters tall. The total area of the building is 400,000 square meters, is 9 kilometers away from the city center, and 1/3 of the site area is left to the public use. The tower itself is mostly office space for Gazprom group, and then there's an observation deck at the top of the tower. It's housed within the spire itself that has panoramic view of the city center and also the Gulf of Finland. The multifunction building, as I mentioned earlier, it has multi-use, is very complicated. And from this picture, you can see there isn't really one floor, as you go around the building, that has the same dimension. So practically the only way we can execute such a project is to fully utilize BIM in every aspect to ensure full coordination. Now, definitely the location of the tower in itself, as you can see, it's lonely, but it's very well connected. It's inspired by St. Petersburg historical spires. It would be definitely a catalyst for development of a new futuristic architectural landscape, and it's a polycentric development. It has become a postcard since its completion, so it's been a tourist attraction and will contribute to the industry. I think many of the industries and businesses are moving into this area, and definitely will be a catalyst in accelerating the district development to a new business development. Now, the project team in itself, the developer is Gazprom Eastern European Projects, and the project will be occupied mostly by Gazprom Group. The project has a really very interesting history. Our MGM, when they won the competition, they did only that for a while. And then at the later stage, when it moved from Okta to Lakhta, they also developed the concept for a taller tower and a much bigger area. And then later on, RMGM essentially didn't do much. Gorprak took over the project, and they did the schematic design and partial DD. And then the project went for bid, and Samsung became the general designer and the construction manager on this project. So Samsung is the general designer on this project for everything: architecture, structure, MEP, facade, basic detailing, and Gartner were involved before we did in terms of working out on the detailing of the facade that is very complex. We worked this project in collaboration with Core Project, and during the due diligence review of this project, we use SMDP to work with us in reviewing the design and make sure we got all the pieces from architectural and structural standpoint and identify any potential problems. Now, what does general designer mean in Russia? That means almost we, as Samsung being the general designer, we develop working documentation, and the working documentation is essentially doing the shop drawing, coordinated set of shop drawing that handed over to the contractor, where the contractor didn't need to develop really any shop drawings. They use the drawing that we developed for them to build from, except for performance-based design elements such as the vertical transportation and the facade. So Gorprak worked with us throughout the process to complete that. And also the contractor for the entire project is Renaissance Construction Company. And we also, since we're construction manager, we developed a very detailed construction method statement how to build this project, in which we shared with Renaissance. Now, the Lakhta, as I mentioned earlier, is not only a height breakthrough. It's a breakthrough in integrating the latest technological advances in material construction methods, innovation, and bringing some of the best international and local standard and practices by engaging global teams and experts from everywhere. We have more than 600 companies that participated in this project, and we have more than 20,000 people from 18 countries that applied their best practices to execute this project. And also engaging of major international consultant, contractors, subcontractors. So practically we brought a lot of new materials, from Europe in particular, and some of the major contractors in the facade, such as Gartner, which I will speak about a little bit before. So integrating all of these elements by bringing this practice, Samsung had a really important role to play, just to make sure that all of these people from different background, experiences, expertise, to develop something that's fully coordinated was very important. The project itself is inspired by nature, it's organic. And then the building form has a sorry about that. The building form is organic by simple. The entire building consists of 5 leaves that are prismatic, that it twists about their own axis, about 90 degrees, and then widen at toward 1/3 of the building, and converge at one point at the top of the building to form the spire. And so the spire is a continuation of the shape of the building. As you can see from this one, it's really very challenging from structural, how to engineer such a building. The spire itself is about 170 meter tall. It's about 60 meter at the base, and its total weight of it from structural steel is about 2,000 tons. The multifunction building itself, it's complex in its own right. As I mentioned, we can have another long lecture what we had done for this particular building. And as you can see, the roof in terms of sloping and collection of ice and snow, and how we managed that one was also very challenging by itself. So we introduced ETFE, like a pillow kind of system that allows light and doesn't allow formation of ice on this one particular. This one is the atrium of the multifunction building. The multifunction building has also a double skin facade to mimic that of the tower. The amphitheater, it will be open to the public use, and I'm definitely sure it will be a place where many important events will take place that will people come and be able to enjoy the site. Now, what we have is also in the building an intelligent, what we call is a buffer zone, which is double facade that are used at the corner between the edges of the petals. The spaces between the facade are kind of glazed balconies that can be naturally ventilated. There is no major air conditioning or heating in this area. And this area is equipped with vents and valves which automatically open to a certain climate conditions to control the temperature. As you can see on the right, the flow of air in and out naturally through vents. The buffer zones occur throughout the tower. They are double height areas, and people can access these, and it's not so big, but they can have access to it, and they go up to level 73. Now the tower facade, which I will speak about later, because of the shape of the building and constantly changing, it all bent with glass. It's very expensive, but the client really wanted it, and they had worked very closely with Gartner in developing the system. So almost 70% of the facade elements have different shapes, and each of the units weigh about 800 kilograms, and the floor-to-floor height is about 4.2 meters. Because of the shape of the building, we have special rails that climb along the edges of the tower from the corner, and they climb up and down the building. And these BMU essentially travel on these rails and change dimension as you go up and down the tower. And these can be used for not only maintenance, but also replacement of glass. And it doesn't take very long time to travel. So because of the shape, it was very difficult to find places where we can have a PMU in this one. We did propose a few ideas, but the client really wanted to use the system here. What we have is the facade lighting is also located at the corner along the edges, and it does project the light, and they are LEED Platinum certified, so they don't have any light projection. It's just the light coming from the corner flood the tower, and it's really working beautifully. Now, some of the challenges that we have, the top of the spire is pretty much open, and as you can see, it created opportunity for the ice, wind formation, and the question is, how do we control that to make sure that the ice and the snow doesn't fall down and hurt people? So we actually developed a system in which we captured all of that and managed it. And it's been through several cycles, and it's been very effective and safe. Again, we have a complex geometry, and we have the soil conditions. We don't have rock, it's sandy, stiff soil, clay, very stiff sandy clay. Some of the basic, some of the building innovations that we have big data, in which we used survey and real-time structural health monitoring program for the entire building to measure, and it's all the building behavior, and it's fully operational right now. The facade is naturally ventilated, energy and efficient elevators. They have energy recovery of energy during braking. Ice generator that is used, it does save energy, smart waste disposals, and we have, as I mentioned, ETFE at the multifunction building to prevent ice from formation. And now this project is LEED Platinum by international certification standard. One of the things that is unique about this building is talking about the structural engineering design. For example, from the onset of the project, we developed a strategy, structural engineering strategy, how to approach this project. First, we needed to make sure that the structural solution integrate with the architectural fabric, maximize exterior views, minimize the number of exterior and interior columns, so we don't have, we can manage it better. continuous structure throughout the building height, no transfers, and also utilize all the elements to resist the lateral loads. And we were to maximize overall building stiffness without needing any additional material. That means we didn't need to upsize any of the member beyond that's required for gravity. Again, robustness and redundancy was developed as part of the design concept. But the most important thing that we had to deal with from the very beginning is we needed to develop a system for constructability to avoid the complex detailing. And also, we wanted to, because of the different aspects and the distance between the core and the outside, you will see differential shorting was a big issue. But one big advantage that we have is related to effectiveness of the building shape, because it tapers, twists, constant variation, the edge conditions. We have a vented spire at the top, so we didn't have any issues related to mitigate the wind dynamic effects, and that also resulted in reduction in wind forces and acceleration and the torsion of the building. This is just a quick view. As you can see, the location of the column at the exterior, they do not compromise the interior space whatsoever. So you have a complete freedom to do whatever is needed from architectural planning standpoint. Level 19, 35. This is an area where you see here is the buffer zone. So there is the column, there is no floor here. So you don't see that column in there. At level 56, at level above level 61, we have only 10 columns that continue from the base. And as we go up. Now the building form, definitely, as you can see, the column is really special because we didn't go with the straight columns. So essentially the column followed the profile of the building. And what you see, the edge of here represented the column shape. So they are actually curved, but they are built as a straight segments every 2 floors. Because the variation was not so big, we were able to deal with it structurally standpoint. As you can see here, this is the architectural shape from the outside. The structural column follow exactly the profile of that, and this is the actual shape of the column. Now, this definitely every floor, the transfer of load from every floor and the change in geometry resulted in a horizontal forces by axial into the floor plate. So we looked at that very closely, and we looked at the torsion diagram every floor, and then looked at the cumulative torsion that taken by the core. Now the core is round, strong torsionally, and also stiff torsionally. So we were able to deal with these very easily. But as you can see, the transfer of load is not only through the beams, the major beams, but also through the slabs. And around the perimeter, we created what we call a structural ring, in which we are able to transfer these torsional forces into the core every floor. Now, the lateral load resisting system of the tower consists of a centrally located 26-meter diameter reinforced concrete core that is linked to 10 to the exterior column, the 10 exterior column through a 2-story equally spaced outriggers at 4 levels. And 1 story at level 83 at the top. Now, one thing that is very unique about this one in particular is that the outrigger doesn't penetrate through the core. And we did the same thing in Jin Mao Tower at the top of level of the at the last outrigger, where we also had a core in which we introduced an external ring to transfer the horizontal forces of the top and bottom chord of the outrigger around the core. So we used the same technique here, and that resulted in a significant improvement in terms of constructability, in terms of saving money, in terms of avoiding complex detailing, and then also took the outrigger from the critical path. So this is one of the new things that we're looking for, and at this moment it's like what I would call is like a beam column joint, where you have a pipe section and transferring the load through an outside diaphragm. We use that typical detail. It's same thing is applies, and I think it's a new system that I think it could be investigated in other tall buildings. What you see here at the corner is the Jin Mao. As you can see, we created a ring that ties everything together as a secondary mechanism to transfer the horizontal loads through floor diaphragm. As you can see from here, all the forces are transferred to the top and bottom chord and get dissipated into an outer ring, which is about 1.2 meter thick. So the top chord is composite, and which I will speak about a little bit with the detail. This is essentially what we have is the outrigger is only have a single steel column embedded in the core. We have the composite column. We build the floor and leave the outrigger to build at a later stage. But all the elements were there. So we continue the steel construction without interruption. What you will see here, this is the outer ring that transfer all the torsional forces at that level in particular, and the horizontal forces from the outrigger through a ring around the core. This is the detail essentially of the outrigger. So what we have is a steel column embedded in the core. This is the composite. This is the composite column. This is the steel column in the core. All the diagonal take all the shear, and the top chord take all the tension. But we have a very stiff composite top and bottom chord that contributes significantly to the overall stiffness. It's just a reminder of we use the same concept in Jin Mao, where we were able to create a ring as a second line of mechanism to transfer the horizontal forces of the outriggers. The outriggers were extremely effective in reducing the bending moment in the core by 50%. But however, there was an increase in the column load by 25%, but that didn't require changing the column size beyond that, or the core size beyond that required for gravity. This is just some of the composite details. As you can see, the outrigger doesn't take any gravity load per se, but we have beams around the composite section and left the outrigger unconnected for some time. And later on, we were able to do it whenever we wanted. Now, the wind engineering, definitely, like every other project, we did have high frequency model, pressure integration model, cladding test, pedestrian wind study, Spire studies with the different set of openings because it's evented. So we work very closely with RWDI related to this issue, and also Spire full-scale icing test, dry and wet snow. One interesting thing related to the pedestrian wind, this is an open terrain, open to the Gulf. There is nothing around it. The building shapes are conducive to speed up the wind. So we ran into some challenges to make sure that the comfort level for pedestrian is fine. So we work with RWDI very closely to mitigate the wind effects, to make sure it is comfortable for people coming in and outside the tower and for typical use, especially in the open plazas. Snow and ice test. We did full-scale model to test dry snow, wet snow, in-cloud icing, and how to manage that. What you see here is when the snow or ice is formed, essentially what we have is a capture to capture that, and this it has a system to melt the ice. So we don't at every level, so to prevent any kind of falling ice down below. Again, the shape of the building, as I mentioned, it's very close to square. In fact, it is much better than that. The building drift for wind load was about, at the top of observatory, about 500 millimeter. and the top of the spire is about 800 millimeter. We also looked at construction sequence to look at what is the gravity displacement of the building. Again, most of this work is done by Samsung, is about 81 millimeter. And the building settlement, like every other project, geotechnical engineers tend to be conservative. We have a local geotechnical engineer that gave us the subsoil stiffness in which we anticipated 100 millimeter of displacement. The building period is about 8.65 seconds. The torsional is 2.5, so there is a huge separation between the translational and torsional mode, which was also another benefit. For typical floor framing, this is typical architectural plans. What you see here is a typical odd floor. We have a composite girder only at the major areas, and the rest of them is about 400 millimeter composite beam. The slab is about 60 millimeter foam deck with a 90 millimeter reinforced concrete topping. This is a typical even floor where we have the atrium every 2 floors. So essentially, this area will be, sometimes it's very small, it's not really much you can do with it, but in other areas it's big enough to be utilized. This is just construction photos showing the steel framing, and also you can see the deck, so it's pretty open space will be for architectural use. In terms of the composite details, which is very interesting, as you can see, the columns straight over 2 floors. We have a big plate here, and in this plate we have an extension in which we accommodated the change in the shape, and then the splice was straightforward, and then we followed up with the composite construction. At the beginning of the project, when we took the project, we had a really solid steel columns, was designed by Initial Design, which is roughly about 850 by 850 solid steel column. And when we came in, it was, we thought constructability wise will be problematic. So we proposed several alternative columns systems, and we saved more than about 10,000 tons of steel in the building, including the floor framing. It's just some of the construction photos. Now, in terms of the core, again, it's very really tight, is very well designed, and is very, very highly efficient. And one interesting aspect I didn't talk about is we, from the floor framing, I will not go back, but we minimize the number of shear taps that goes into the core because as the floor twists, we don't want to have a lot of embeds into the core. So we minimize that, and we were able to minimize the number of embeds so we can have easy to follow. As typical, we used the ACS formwork system, Perry, for the project. This is what a typical core framing look like. Most of the load is taken by the perimeter of the core. All the walls within the core itself, they are 250 to 300 millimeter maximum, and all the load transferred to the perimeter. For a typical, from level 7 to 85, we have only 800 millimeter thick wall, and up to level 57. And as we go up, the thickness of the wall at the perimeter, it was about 400. We use C80 concrete or B80 concrete, which is a cylinder strength, and it's the first time it was used in Russia. Same thing with the composite column. They didn't have the Russian standard, didn't really have a standard to do composite design, in which we have to do a test to show them, and we supplement them with a lot of information. But finally, I convinced them that this is we'll design it as a reinforced concrete to maximum amount of steel that is allowed by the code, which is about 15%. So it was much easier to pass the expertise. Just construction photos of the core. The other one is the Spire structural steel brace system. As you can see, we were very unfortunate. We hit the construction in the winter time, and where we have all kind of issues to deal with. And the wind speed typically is about 15 meters per second, in which it affected our productivity a little bit, but we incorporated that into our initial program. The spire essentially consists of 5 braced frames that taper to follow the profile, and all the other elements, because they changed shape around the perimeter, they're all part of the facade. So the connectivity of the exterior facade connect to the column only. They don't connect to the horizontal beams. And that allowed us to quickly go up. These columns are a continuation of the spire of the tower column, and they continue through, as you can see here, at level 83 all the way up. At the top, it became very small, so it was a single pipe and hanging plate from it. We did look at this construction of the spire, the top, especially during winter time, and we did look at the construction sequence analysis that was fully adopted by the contractor. The tower foundation is very unique in its own right. The tower is sitting on, again, this can be a lecture on itself. The tower is sitting on 264 piles, and because of the core shape is very small, we couldn't have enough pile under the core, so we need to spread the load out. We introduced what we call is a box shaped foundation. Which is pile supported box foundation system, which I'll speak about a little bit more. Fortunately, the site was really completely dry. So when we did the boring for the pile, or the we have a followers, but because it reminds me of Shanghai, where we had a very stiff sandy clay, where at some point you didn't have any water that can penetrate through this. It's just impermeable. So we were able to build the piles on the dry. Essentially, this is the bottom of the pile, which is about 85 meters from the surface. Practically, it was completely dry. So the tower is sitting, as I mentioned, is 128 piles, 2 meters in diameter, extends 65 meters below the raft. Within the tower footprint, and then we have about 136 at the perimeter. Again, this is very stiff skull. For me, I think it was very interesting detailing that was done by the local geotechnical engineer and Borprak and Enforce before we started on this project. So essentially what we have is the load from the core and the column. We introduced this very rigid box consisting of a lower plate, 3.6 meter, top plate, 2 meter. It could have been thinner, but it was a little bit on the conservative end. But the load essentially transfer through this very rigid box to bring the load to allow for a better distribution of the load to the piles. However, when we monitored the building, as usual, the soil was much stiffer. It acted like a rigid block, in which the initial settlement was expected to about 180 millimeter, and the real one we have only about 40 millimeter. And almost, I would say, the stiffness initially was assumed to be 15.5 ton per millimeter. We have roughly about 40 ton per millimeter, which means we calibrated this to look at the construction sequence of the project. Now the raft, the 3.6 meter raft, was built in December, winter time, very harsh condition. So we encapsulated the entire site with the weather shelter against rain, snow, and also to maintain the temperature within 10 to 15 degrees. We used P60 self-compacting concrete, and it was poured in a single shot, about 19,000 meter cube in 49 hours. Just some of the construction photos of the raft. Now, the other thing, from the onset of the project, we developed a very detailed survey and structural health monitoring program. What you see, the middle section essentially define everything you need to know about the survey and the health monitoring program. We have strain gauges located above and below the outriggers on all the columns. And then we have strain gauges in the outrigger. And then we have accelerometers at the base and all the outrigger levels. And we have tilt meter to ensure the verticality of the building as we build the building. And also we have a weather station at the top of the spire, including accelerometer and GNSS system. In terms of the strain gauges, between the tower and the foundation, we have more than 3,000 strain gauges that's fully connected to a central data logger system. A lot of analysis has to be done to really fully understand. We also looked at the composite section, in which we installed strain gauges in the steel column, rebar, and the concrete to look at the transition of load with time through those. And we did look at the detailed construction sequence step by step. It took about 4 days to run such an analysis. And then based on the calibrated stiffness of about 40 ton per millimeter for the raft, and we looked at the building deformation during construction. The red line is what we predicted, and this is the actual one. There wasn't, because of the core and the mega column and the column, exterior column controlled by gravity, we were able to manage the differential shortening very, very well, in which we didn't really need to wait long to connect the outrigger, which was a huge benefit. Now, this one, these slides are really coming from Gartner. You cannot see their name, but they've really done a fantastic job in dealing with the complex geometry of this project and simplified both the design and the detailing. So as I mentioned earlier, the facade area for the tower is roughly about, oops, excuse me, this keep moving around with me. We have about 10,000 square meters is all bent glass, and 70% of the facade, they have different elements. So the complexity of the tower, so each of the shape is parallelogram, is about 2.8 meter by 4.2. With the bent glass, essentially we have to push about 30 kilogram to get about 4 centimeter of the formation to get to the shape of the building. And that's done all in the factory. And unitized facade system, this is the yellow here. And also we have 3 different types. One is the exterior facade, and one is we have in the buffer zone the interior facade. Again, we have tempered glass and optimized with different supplier, and also the quality control and production was extremely important. This is the way it was before in terms of behavior, and this is what Gartner proposed for an optimized solution. Again, as I mentioned, the buffer in the buffer zone in particular is a very special one. We have 5 atria per floor, and the buffer zone allow for natural ventilation, in which the louvers have to automatically open, as you can see from these photos to the right. And then in our facade, between the buffer zone and office space, they are pretty simple, and we have operable window where somebody will have access to that. So these are pretty straightforward detail inside. Now at the corner of the building, we have vents throughout the tower, in which we bring fresh air into the building, and that tucked pretty nicely within the column enclosure, so it didn't have to impact the overall look of the building or the inside space. But also, as you can see here along the height, we have a rail in which the climbing BMU system will attach to these points. So these mullions at the edge, they supported directly, very close to the column, very rigid, and we were able, it was a bit complex, changed a lot, but we were able to come up with the detail that allowed that to go. In terms of the spire itself, it's stainless steel. As you can see from here, the total is about 13 metric ton. It did include the LED lighting, aviation lights, and T tracing. And the spire facade is also stainless steel mesh for the itself between these vertical elements, and is designed for snow and performance, as I spoke before. This is a reality, what we had seen on the project, and how we managed the ice and capturing the ice. It was a pretty safe and a pretty robust system to make sure that it doesn't fall down. And we have collectors every floor, so it doesn't let accumulate. And we have a heat tracing to make sure that these at the parameter of these ledges to melt the ice as soon as possible. We did a full-scale test on that, and these are what you see here is the areas where we capture any falling ice every 4.2 meter. Production of the facade at the factory. Gartner will be speaking about this at the Council on Tall Building and Urban Habitat for best facade. I think I will not spend too much time. They are the experts. And here is the installation. And this is just some of the site impression installation because of the shape during construction. So it was pretty tough, but we were able to manage that and deliver on time. As you can see in some areas where we have the outrigger, we use a pop method, similar to what you used in Tower Palace 3 and Burj Khalifa to skip the difficult floor and come back to them later. Just installation of the spire. Now, just quickly, the project is still, the interior is being finished. The core and shell is completed for the entire project. It's been commissioned. But there's still some interior work ongoing. These are some of the elevator lobby, entrance lobbies, wave stairs within the lobbies also. And this is the tower entrance, another level. Third floor entrance lobby, and there's some unique stairs over there. And here we have the arch. Within the arch itself, yeah, sorry, this is still in the tower lobby, but near the arch where we have a monumental stair that really goes around. This is the observatory at level 83 and the observatory at level 86. In terms of the multifunction building, as you can see, is extremely complex. Also, we have the planetarium is over here that's projected into the atrium. And also the multifunction building atrium essentially doesn't have any use, but it connects the two sides of the multifunction building and the program together. Some construction photos, PAL installation. It was pretty nicely, very high quality, accurately. It was done by Power out of Germany. This is the PAL completion raft. Weather shelter to install the raft under severe weather condition with good weather protection. We use about 18 pumps with 5 reserve to pump the concrete using self-compacting concrete. Core installation of ACS formwork system, steel framing, deck installation, installation of the facade. Completion of the frame of the multifunction building and the arch. It's just construction photo progress. Completion of the spire, pinnacle. And then the project, now the crane are coming down. Completion of the multifunction building with a double facade. And these are just some of the shots of the impression of the building. It's really, for me, when I look at the building at this moment, it's just like you have this building that consists of a mass and like a ship sailing into the Gulf, you know, and it's just very well connected, and it will definitely attract a lot of businesses in the future. As you can see, since we started the project, many buildings started to build around. So. And lightning is always a test, and this is the completion of the project. Now, I had a short video, but because of time, we just didn't show it. But Carl mentioned, recommended that I'll take a look at, we also involved, now we went from the north hemisphere to the south hemisphere. This one is Merdeka 118 in Kuala Lumpur. So again, the building is very complex, but working under completely different conditions, from North Pole to the South Pole. And you want the freezing to hot the climate. So it was within the same kind of period, and these two projects were working at the same time. The program is pretty complex. It's very nice because it's a near stadia, which has a very, very importance from historic standpoint. And the design essentially brought the tower and integrate these important facilities as part of the design. It's consistent with tower, residential, retail, and this is landscape open to the public, so people can enjoy the Merdeka Stadium and also Nagara Stadium. You know, for people who work on 118, actually Plaza Rakayat is not too far from here, is nearby. This is just some of the expected completion, what it look like, access to the public from the retail into the stadium. And this is where we are today. And I think for some of you, I have given a detailed presentation for Institute of Civil Engineers in Malaysia and UK, which I think would be, you'll be able to see that it's about 1 hour presentation goes into the detail of the structure. And with that, I thank you very much for your attention. I'm sorry, Carol, if I went over my time. I really apologize for that. Too much to say, but it's too complex. And even with that, we couldn't really cover all the issues associated with the complexity of the project and how we dealt with it. Thank you very much.
Well, thank you, Ahmad. It was absolutely fantastic, a really beautiful building, and so incredibly complex, as I think that even the most lay of lay people listening to this talk can begin to have a point of entry of the myriad things that you need to think about and anticipate in a project like this, from the foundation piles to the melting of the snow of the spire. We are very late in our time, but I do want to ask, you know, a few questions and promise people that there'll be another hour probably on Merdeka as such a fascinating counterpart in so many ways to, as you say, the South Pole and the North Pole in terms of their climate, but in the site development of landscaping and cultural buildings that form a complex around a signature tower, a kind of defining spire, those projects seem to me very similar in their development. And I think I may have failed to mention at the beginning, as I introduced you, that you're speaking to us from Seoul, South Korea tonight, except it's Wednesday morning for you, and I think not just almost breakfast time, because Ahmed came onto the screen this morning before he went to bed for about, I don't know, maybe 3 hours in order to do a practice run where I said, oh, we really have a lot of slides here, so maybe we should cut out a part of it. But it was so rich to see so many aspects of the structural problems and the constructability problems that you need to deal with. It struck me because I'm familiar with the complex history of the design, the site even, orienting it out of the historic city, the succession of clients as well as construction, as architects and construction managers, that one usually describes a building that is, or a project that is designed by committee to the extent that this one brought on so many different people in the design phase. One usually thinks of that as, you know, a camel is a horse designed by a committee. But in a way, this building became a kind of, not a camel, but a kind of a gull. I mean, it reminds me as much of Brancusi's sculpture as it does any other kind of organic form, something like the idea of flight. And I think that your animations in particular really showed us that architectural evolution of the form. It looks like an extraordinarily expensive building, and you suggested both some of the savings that were made, as well as the investments in materials like cold bent glass that we know few projects use because they're so expensive. Could you comment a little bit about that aspect?
Yeah, I think for one, I think, as you know, RMGM was developed the design concept, but they went out of business, developed by Gorprak, and then we end up being the general designer. So in some sense, it was left kind of, we have to look at the original design concept and make sure that we fulfill the vision with the very limited information that we have was rendering. By the way, most of the interior design is done by Exclusiva, which is an Italian firm in which they really developed this fabulous, fantastic interior, very expensive, very rich design, in which we had with the free-form architecture by itself, in which it was a challenge in its own right. I think, as I mentioned earlier, when you look at the component, one thing, the exterior is complicated, but when you look at the interior, is equally complex. So anyway, I think historically, I think at the end of the day, as I mentioned, we were able to bring a lot of people with different expertise from different countries, different backgrounds, different culture, and into one melting pot in which we needed to develop a design that is fully coordinated, in which the contractor didn't need to worry about the shop drawings. And that what really helped the client to control not only the budget, but the schedule, because we didn't need to worry about it, because we as a contractor, we were able to make sure that everything we produce is a fully coordinated set of documents that the contractor just need to build it. And that resulted in delivering the project within budget and within time.
I mentioned in the introduction how many super tall projects you've worked on in your career, from your very first jobs, I guess, at SOM, through the Burj Khalifa, now heading this project for Lakhta, the tallest building in Europe, the Merdeka 118, the second tallest, soon to be second tallest building in the world. Could you reflect a little bit on your career over 25 or 30 years, and how, as you said, you made a connection in terms of a structural idea taken from Jin Mao that was applied at Lakhta. I wonder if you could, kind of reflect on your experience.
I mean, yeah, definitely SOM is an institute. I came back with a civil engineering background with a structure, and I learned so much. It's a rich environment in which it allows you to think beyond of what your comfort zone, and you have to fit within an environment in which you can contribute to many things. And I always, through my experience at SOM, we always think the way of how you build a building. So before you design, you need to know how you build it. And if you don't know how to build it, that means you have to think it over. So taking a complex element and develop it into a simple design, it takes so much effort and so much ingenuity. And that, what I learned a lot at SOM, is how you first not to make it complex, but at the same make it simple. So whether you go from Jin Mao, we designed for constructability, because we knew in order to meet the time and the budget and any kind of hiccups, we've got to develop a system without events, without changes, without transfer. So continuity is extremely important. And that was, if you go from project to project, the projects that we face, the most difficulties is where you have this change in systems, in which it resulted in a lot of not only technical issue, but cost and time and so on and so forth. So through my experience from design into construction, I spent about 18 years in construction worldwide. So we always able to transfer the technology from country to country and make sure any project we touch, we bring in the best practices to help the client achieve their goals. And that is something, whether working in North Pole or the South Pole or the Middle East, there's a shared experiences that we can bring in. For me, I think always you need to identify all the problems, especially in construction, and you need to come up with a solution that works, that works, that you're confident that it can be executed without problems. And design for construction. And now the new theme actually we're doing right now, not only going to construction, we have a special R&D center designed for manufacturing and construction, which right now it is something that to increase the productivity, to increase safety and all that kind of stuff. So that required the development of new systems. And that's what we are working on at this moment. So mixing design and construction has been always in my blood. So I think when you look at the project, the first thing you need to know, how fast can I build it? And are they using the latest technologies? What benefit does it have to the client? And that is something we encountered in 118, in which you take a building shaped architecturally, in which resulted in wind forces bigger than the environment that it is in, and bigger than wind forces than even Hong Kong, which is kind of a little bit, you think, wow, what the shape is really makes a big difference. And that is something we learned at SOM. To save money, you need to think about all of these things at the onset of the project. And that went with me for a long time. Spending a career at 16 years at SOM took me a long way, actually.
Well, relevant to SOM, I have to tell you that your colleagues are on the Zoom tonight. So Bill Baker has a couple of questions for you already. Mark Sarkeesian is on the Zoom meeting, as is Pete Weissmantel. So it's all your colleagues from SOM are keen to show their compatriots in this discussion. And I have to mention too that in part I think what's so fascinating to me as a layperson about the engineer's mentality is the kind of constant appetite to deal with questions and to clarify definitions. So I'm delighted that our other speakers are with us on this Zoom and that they're saying, you know, hi to their friends. But Bill also has a question for you that I'm going to read. He says, ask Ahmed about teaching at IIT with Myron Goldsmith and David Sharp.
Oh, that was really a big pleasure. I mean, for me to, when I was young, I think Bill and Majoub and Mary asked me to work there. And we really always, it was, you know, really just everything we've done, I think with the students is a practical design in which we brought a lot of experiences. And it was really a place where we had the opportunity to do R&D. For example, when I was there, I took on myself to look at the wind engineering. Why, you know, at some point, architect didn't like prismatic building and they wanted something more interesting. And one of the things that we wanted to do at IIT was, okay, in addition to having good structural disciplines in tall building systems, we also start looking at why we cannot use wind engineering, for example, to shape the building to make it better. And this is when we started R&D. And we did the really fantastic type of project, almost to a schematic design level with the students, that translated into how to deal with the wind engineering management, and then at the same time bring that into practice. And some of the ideas that we did there, we brought back into practice, and including Burj Khalifa, including World Trade Center, including some other things that we see today that has shown a huge benefit in terms of design. So it was really, and now actually I'm teaching at Seoul National University. I'm a adjunct professor also here. So I teach one semester a year. Tall buildings and long span structures vary year by year. And also it's very rewarding because one of the things we like is working with the young engineers with the new technologies and how to utilize that and implement it into what we know and continue to develop new ideas and new systems. But definitely now the trend is how fast and how quality and safety and material use and, you know, and all of these things, it is will definitely have a major impact on the structural systems that we're developing nowadays, for sure. So it was a great pleasure for me to work with Bill and David Sharp and Myron. I learned a lot, so much from them, how to think in terms of keep things simple. Yeah, and use the least amount of material, always. Yeah.
We thank you for teaching us a lot tonight, and we have a lot more to learn. Maybe we'll return in another season to constructability and have you give us another hour on Merdeka as it's as a completed project. But I think we've only just begun to open the door to the issues of the professional expertise, but also the design innovation that's involved in actually the construction process and planning that process as well as executing it.
I would like to thank Bill. I learned a lot also from him, working with him. And it was really very great pleasure for me, and Mark Sarkeesian and Bob Sen and Peter. So we did have a long history, and almost I would say every project has been really successful, especially Burj Khalifa. We worked like very tightly, worked together to, especially under his leadership, to develop something that's really very unique. You know? So, yeah.
Well, we thank you so much for tonight. We need to wrap up now.
Okay.
New Yorkers need to go to dinner and you have to go to breakfast. So we thank you for extending our worldview to South Korea and also to St. Petersburg. We ask everybody to come back and join us next week when Fred Clark will reflect on the history and also the lessons learned from the Petronas Towers. Back in Kuala Lumpur, again, for our worldview. So Ahmed, thank you so much for being with us.
Thank you, Carol, I think, for inviting me and for your interest in what we are doing. And really, I also thank for the Skyscraper Museum for sponsoring such wonderful programs that definitely go a long way, especially in education. In fact, I'm encouraging most of the students, graduate level class, to tap into the Skyscraper Museum and learn about the history of tall buildings. So we really appreciate everything you're doing. It's wonderful.
Thank you.
Thank everybody who joined us to stay late with me tonight. And I give my regards to all. Thank you so much.
Thank you. Take care, everybody. See you next time. Hi, welcome, everybody. It's 6 o'clock, and this is the 12th of our originally planned series of designing global supertalls. We're in the phase of engineering and construction, and our speaker tonight is Ahmad Abdelrazaq, who is the Executive Vice President of Samsung C&T and heads the Highrise Building and Structural Engineering and Global Business Development division within Samsung CT. I'll give a short introduction, but it has a wonderful range of slides that are going to treat us to some of the details of the construction process. And because we had a little preview earlier today of those slides, I know both how rich they are in information and how it's only at the end that he does justice, I think, to this really extraordinarily beautiful building. And so in just a few slides, I want to evoke some of the reasons why we focused on this tower for the almost last, or let me say the originally last lecture as planned of the series. But we are adding an additional lecture by Fred Clark of Pele Clark Pele about the Petronas Towers. That we will, so we return to architecture and we turn to kind of the beginning of this sequence of designing global supertalls, because Petronas Towers in Kuala Lumpur is the first of the global towers to take the title of world's tallest building. So as we began to develop this kind of historical evolution of some of the engineering inventions that allowed for the supertall to rise higher and to spread around the world, it seems now important to circle back and get some of the lessons that we were learning along the way down on the record in order to bracket some of this historical inquiry that we're doing on contemporary towers. And so in our exhibition, Supertall 2020, which we hope will open in June to the public at the Skyscraper Museum, these 9 towers that you see in their slices and their beauty shots are the featured buildings in the exhibition. And there are many more buildings in the exhibition, and there are 59 supertalls in the way that we count them as taller than the Empire State Building, 380 meters. But these particular ones that you see pictured here are, in my view, extraordinarily beautiful formal expressions, as well as innovative engineering solutions to the supertall. And last week, Dennis Poon of Thornton Tomasetti focused on, if you can see my cursor, the Chengdu Greenland Tower that you can see here, and the very innovative design and structural solution to a non-coplanar exoskeleton that he elaborated for us. So something extremely new in the treatment of facades that has been a part of the evolution of the way the super tall has began to develop through fenestration, through formal experiment, and through engineering know-how. Tonight's talk was a way to combine one of the kind of neglected features of the series, which is really to focus on construction, along with a tower that I think is not very well known in the United States yet, but an extraordinarily beautiful one, and that's the Lakhta Center in St. Petersburg. And Ahmad Abdelrazaq is headed the construction for Samsung CNT for this project. So let me go forward a little bit and say that part of the reason that we wanted to focus on buildability and construction is not just that it's fascinating, but rather Les Robertson, structural engineer to whom we dedicate this series, who passed away in February, was my very patient tutor in learning about super talls. And I had the great privilege of meeting with Les many times, and he was a board member of the Skyscraper Museum, where he would explain either current designs or the World Trade Center. And he would always make the point that part of the challenge for the structural engineer and the architectural firm, as those two phases of the design process must work together, architecture and engineering, but that the engineer comes into the equation of the building, the realization of a tall building, by having a strategy not just about structure, but also about buildability. So constructability is always a term that Les emphasized in explaining one of the very important aspects of structural design. And so it's that topic that we turn to tonight. So kind of at the end of this lineup of structural engineers you see here, actually Ahmad is a structural engineer. I'll describe his background in a moment, but we're turning now to this idea of constructing super talls. Do come back next week when the last of the lectures in this coda by Fred Clark on the primacy of Petronas towers will be the subject of next Tuesday's lecture. So the formal beauty, the extraordinary beauty of the Lakhta Center, I think you can see here in just a few slides where we go absolutely, full height and full screen in order to see its sculptural presence, and also its singular silhouette on the skyline of St. Petersburg, because this tower is not in town. It is set out on the Gulf of Finland, away from the historic center of St. Petersburg. And Ahmad will tell us a little bit more about how that site relocation came into the commission and the history of this building. You can see that the town and most of the development is quite far away. And this is a project that stands kind of unto itself as a tower, and with its complementary development of the kind of podium base with the additional uses, which are museums and other things that Ahmad will describe. So one of the challenges of constructability that Ahmad is going to tell us more about and show us in some of his slides are the harsh weather conditions of St. Petersburg, as you can just begin, which are only hinted at here and which you'll see in some of his slides. So as we turn over the screen to Ahmad, who I invite to come on with his camera now, I'll say to you that he is somebody that I've known for almost 10 or 15 years already, because he was involved not just in the Burj Khalifa, which was called Burj Dubai when we did our exhibition on Burj, when it was just under construction. And I met Ahmad then as a part of the team of SOM, who was designing and constructing the tower for SOM, and SOM SOM architecture and SOM engineering. Before that, at SOM, he worked on Jin Mao. So, and I think some of you who have seen Mark Sarkeesian's talk on Jin Mao in our series saw a photograph of Ahmad 25 years ago as a younger man as part of the team of Jin Mao, and he may mention a little bit, make reference to that tonight. He also was mentioned and deserves mention for the tower that is featured in the exhibition and in our series by Carl Fender, the Merdeka 118, and Ahmed and Samsung are the construction managers for that project. And he will give us a little teaser about that at the end and bring us up to date on the construction process, because his talk on Lakhta is so rich that I told him he couldn't talk for very long at all about Merdeka, but we needed to do a whole nother hour on that at a later date. So Ahmed, I'm going to leave the screen now and let you take over, and you will share your screen and I'll leave.